recording? Okay, session is being recorded. Okay. So, as we said before, oh Jesus, the phone again. I forgot to put them away. That's all right. I'll put them in this box as if that will actually do anything. So as we talked about, the Greeks pushed this model of yeah, not really. The Greeks pushed this model of geocentrism. All right. Again, it makes sense under the context of either the stars all make sense and the planets are weird, or the planets make sense but all the stars are weird. And this model was refined. If you know a quick crash course in Greek intellectual history, you had Socrates who taught Plato, and Plato mentored Aristotle, and Aristotle mentored one of the most famous Greek figures of all time, who was Alexander the Great, whose empire had had territories from India to North Africa, all the way up to what is now today Western Europe. And the empire, for its size at the time, was very much responsible for the spread of Hellenistic culture through the rest of Asia and a little bit down to Africa and so forth. So, or at least the northern parts of Africa. So, so when Alexander's empire fell, he carved up his empire and gave it to sort of three little empires to three of his generals, one of which was Ptolemy. And so the Ptolemies ruled Egypt, and this particular Ptolemy created a model in AD 100 to 170 that was sufficiently accurate to remain in use for 1,500 years. Now, I want you to think about that because it's hard to really put it into perspective. So modern science is sort of the beginning. If you pick a start date, is when Isaac Newton, who we'll learn about in a little bit, probably next week, came up with physics. And that was in the 1500s. All right? So that was barely after this Ptolemaic model was overturned. So all of modern science has existed for less than 500 years. And that's going from philosophy to science. Now, modern physics has existed for less than 130 years. And some of the, 100 years ago, in 1920, we didn't know about other galaxies and things like that. So a lot of the information we have about the nature of the universe is only 25, 30 years old. So the knowledge we learn about in this book is not equally old, is the first thing. And some of it is it might shock you how much of what we know happened within your lifetime. And that's what makes astronomy exciting, fundamentally, is we're always learning stuff. And it's the one subject, unlike because when you're teaching introductory physics is important, but it hasn't really changed much in 200 years. But with astronomy, the subject of astronomy at this level, to talk about it changes rapidly, and it makes it really exciting. So after this class even, as you read articles, you will find that things you learn in this class are being revised all the time. It makes it exciting. But think about that, though, getting back to Ptolemy, for 1,500 years, the same ideas permeated. I mean, that's kind of hard to believe, that's how it was. So what did we do with all these Ptolemy ideas? We talked about the epicycles and how kind of ridiculous this was, that planets had these retrograde loops. That was hard to explain. In Ptolemy's models, though, the planets really just go backwards. And what Ptolemy thought is that there would eventually be some explanation for the existence of these retrograde loops. But that we'll see how that goes as far as that being the case. Okay, so I don't want to do this. Let me skip those. So the Hellenistic ideas of the world were in vogue in many different places throughout time. So, of course, ancient Greek culture did not just keep proliferating. Well, I mean, it did in its own ways proliferate and proliferate, but as it spread through the world, as empires rose and fall, it had its heyday in the Roman world, certainly. The Muslim world preserved and enhanced the knowledge they received from Greeks while Europe was in its its quote-unquote dark ages. Al-Ma'mun's House of Wisdom in Baghdad was a great center for learning around 800 AD. With the fall of Constantinople, Istanbul in 1415, Eastern scholars headed back or west to Europe, carrying knowledge that helped ignite the European Renaissance. Why this is sort of presented this way because again, you'll notice 1453. We're getting to the end of Ptolemaic thinking, and we're getting into where the Renaissance, which is what sparked the birth of our modern models of science. I'm going to try using the pen to do this. I think it's all. So we don't want to spend our time talking about all the ins and outs of knowledge transfer through the ages. While interesting, we could do a whole course on that. What we want to do is we want to look at the events of the Renaissance that led to the formation of modern science. And we have an interesting cast of characters. We have Copernicus, Tycho, and Kepler, all right, who are going to look at the alternative theory to see if by looking at the alternate they can come up with a contradiction, and then to see what Kepler concluded, and then how this gentleman Galileo set the stage for Newton to come up with, or Galileo set up an empirical set of criteria about the natural universe, and then that set the stage for Newton to come up with a formal scientific theory, which is pretty exciting. So let's take a look at that. So Copernicus, we're going to have to look at some gnarly looking European dudes. Guy's got a huge nose. So Copernicus, he proposed a sun-centered model that he published in 1543, and he used the model to determine the layout of the solar system in terms of what he called the astronomical unit, or the distance from the Earth to the Sun. That is an important quantity, this astronomical unit. We will come back to it. However, this model was no more accurate than the Ptolemaic model in predicting planetary motion because it still used perfect circles. So it still had this idea of perfection involved with it. Now, moving forward, Tycho Brahe took this from another view. He thought that the catalog of star positions and movements was not accurate to get the discrepancies. So that had been previously seen in geocentric models. So what Tycho Brahe set out to do was create the most accurate catalog of planetary positions ever made. So he made a 1 arc-minute resolution picture of planetary motions. He was hoping that by being more accurate, he would detect stellar parallax, which he did not. He didn't detect it. So he still thought the Earth must be at the center of the solar system, but he thought that the other planets must go around the sun. So Tycho thought everything else went around the sun, but then the sun went around the Earth. And he hired Kepler, who used Tycho's table, Brahe's table, to discover the truth about planetary motion. All right. So Tycho Brahe hired Kepler to analyze his data and thus remove his biases. And Kepler first tried to match Tycho's observations with his circular orbits, but an 8 arc-minute discrepancy led him eventually to this very new idea, which is that the elliptical orbits. And he says here, if I had believed that we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy. So that was the first thing. And I hope the next thing is going from circles to ellipses. Now, if you remember, some rules from being small, all squares are rectangles, but not all rectangles are squares. Well, all circles are ellipses. Oh, hold on. All circles are ellipses, but not all ellipses are circles. A circle is much like a square, is a special case ellipse. Now, ellipses, in general, have foci, or focuses, which I'm highlighting here. All right, you can see them here as well, drawing on them. And they have these two axes. They have this major axis, which is very long, and this minor axis, which is very small. Okay? And they have this property, eccentricity, that is defined by the distance between the foci and the distance from the foci to the ellipse. All right? So a highly eccentric ellipse, the foci are within the ellipse. It is possible to have the foci or the focuses outside the ellipse. Those are not physical ellipses, though. Mathematically, you can do it. But you'll notice that as the focuses or the foci come together, the ellipticity decreases, and when the foci both coincide at the same point, that becomes a center for a circle, and you have a circle, which has an eccentricity value of 0. So what Kepler did is he saw that planets, that if you have elliptical orbits around these two foci, all of a sudden the orbits made sense and worked very well, and the circle didn't work. Okay? We can't do that one yet. So when we look at the orbit of planets around the sun is at one of the focuses of the ellipse. Nothing lies at the other focus. So this focus is the important one. And you'll notice Kepler came up with 3 conclusions based on his analysis of Tycho Brahe's data. So these are called empirical conclusions because they're observed. They're different than a theory because these just make up one part of a theory. A theory has to create a model that describes the empirical conclusions. And Newton actually was able to do this. And we'll just talk about that word in a little more detail because we have to, we generally have to emphasize the difference between a scientific theory, how we use that word in science, and how it's used in the everyday world. I'll put it in my cough drop. Okay, so when planets move in these elliptical orbits, though, it's a little different than a circular orbit, because in a circular orbit, the planet would move. Let me draw a circle really quick. That was a crappy circle. I think I have a shape. Yeah, let's draw a circle inside here. Nope. Hold on. All right, this just got a little silly. I'll delete you, and all right, we can put this circle. Let's put it here. Okay. So if we orbit around a circle, we would orbit at a constant velocity around the circle. With an ellipse, it's a little different, though. With an ellipse, with only the sun at one focus, you actually move very fast around this part, and then you slow down. And it takes a long time to get here. We're just kind of chilling out here, move a little faster, move a little faster, move a little faster, and then it sort of wraps around and then slows down. Okay? So the velocity is not always constant around an ellipse. And I have to tell you, in general, circles are easy, ellipses are hard. But nature doesn't care about how easy math is. Okay? So Kepler's second law relates to that, which is that you'll notice that you move, if you look at these two shaded regions, here's shaded region 1, shaded region 2, and we can actually see that if you start a stopwatch and measure it for some t, we'll call it T1, and we'll call this part here T2. Now if, we'll call this A1 or A2, we'll call this A1. Now Kepler came up with this, Jesus. I am all sorts of bad today with the alarms on the devices. Sorry about that. So if we look here, right. So the idea is that this can be shown, that motion I was explaining to you, by noticing that if these two times are the same, hold on, if T2 equals T1, then A1 equals A2. All right, so that means that if this takes 30 seconds and this takes 30 seconds to sweep from here to here, and this takes 30 seconds to sweep from here to here, these two areas, as complexly different as they look, are the same. And so the indication here is that the planet, as I said, will move much faster here, in this part, when it's near the sun, than it will away from the sun. Okay? We can't look at those either. Now, Kepler's third law, and I don't like how this is written, because this is, I mean, I know we're not using a lot of math, but we can at least be honest about things. This should really read P squared is proportional to A cubed. All right, now P, why this means, this weird fish-looking thing means proportional. It wasn't until Isaac Newton that a real equality could be formed. And that's important. That's, even in math, we knew that difference back then. So basically what this says is that the orbital period in years is proportional to the average distance from the sun in AU. Remember the ellipse, if we look at the, if we draw an ellipse again, let's make a circle. That's pretty good. And let's make an ellipse. Okay. Now, unlike a circle, the circle's here, where you have just the constant distance to the center, with an ellipse, the distance isn't always the same, right? When you're at this end, you're much farther from the sun than you are here. But, so you have to take an average distance, or an average distance to apply Kepler's law. And what you can see here is from here that if the distance increases, the period also increases. Now, this is hard to see, but we can make a little table to see exactly what that means. So let's do that here. So let's take a look at the Earth, which is A. Hold on, I need 4 columns here. There we go. So here I'll have A and P, and then I'll have P squared and A cubed. So let's do this for let's have 3 pretend planets, and we'll do this for the distance of 1, 2, 3, and 4 astronomical units. So in order to find P, that's actually quite challenging. So let me switch some of these around in a way that makes sense. So we'll move P here, so we can get A. Whoa, right. A cubed, and then we can get, from there we can get P squared, and then we can get P. All right, so when we look at this here, so 1 cubed is 1. Oh, right. 1 cubed is 1. 2 cubed, 2 times 2 times 2 is 8. 3 times 3 is 9 times 3 is 27. And 4 times 4 is 16 times 4 is 64. All right, so these are equal. And now we want to take these numbers and take them, we want to say that they're also equal to P squared 27, and 64. And if we take the square root of these numbers, we'll at least get 1, 4, or hold on, 2 root 2. 27 is 9 times 3, so 3 root 3, and 4, and then we have 8, right? So we can see through these numbers that as the distance increases, the period gets longer, right? So what we can say is that basically what we can see without getting too complicated here is that the farther away you are from the sun, the slower you move, the longer it takes to orbit the sun. And this is going to be critically important to understand dark matter later in the semester. All right, so there's a reason I'm focusing on this now. It's going to come back and be the first indicator that things are not as they seem as far as matter in the universe goes. And it's important to have one part of the model, and then and what you have to do is if something doesn't behave like this, you have to, and by this I mean like here, then you have to add something to the model or refigure things out, which is what scientists have been currently doing for a long time. So going through and moving on, we can't see this. So you'll see here, this is an easier graph to see. You'll notice you have the average orbital speed in kilometers per second and the distance from the sun. And I want you to notice, again, what I was saying, understanding this graph and why it works, which is from Kepler's law, third law. So you'll notice as the planets get farther away, their speed decreases. Understanding this graph will help us understand why we think dark matter exists later on. Okay? So let's keep going. Are there any questions so far? This would be a great time to ask, rather. I feel like I've been talking. And unlike being in person, I can't always read where you're confused or not confused. Okay. So, everything good? Yeah? Okay. All right. So, okay then. So let's move on to our journey. I already saw that. I already did that. To Galileo. Now, Galileo, as you can see here, is holding something. Where's my damn? Oh, that's why that's not working. That happens sometimes. Galileo is holding something here that changed our understanding of astronomy completely, which is the telescope. Okay? And he overcame the major objections to the Copernican view. 3 key objections are rooted in the Aristotelian view that we're following. Earth could not be moving, so because objects in air would be left behind, we have to explain that. Non-circular orbits are not perfect, as heaven should be. There's some debate about how important this whole perfection was to the Greeks. I think they were willing to let go of it, but some might have argued for it. And if the Earth were really orbiting the sun, we detect stellar parallax. So this one we've talked about is the big one, right? That's something that's measurable. This is actually an interesting point. I want you to imagine for a second that, let's see, what do I have here? I want you to imagine for a second, if you can see me, that you imagine this is a bus, this puzzle wine glass thing I have, all right? If you're riding in the bus, if you're riding at this point in the bus and you jump up in the air, does the back of the bus come and slam and hit you in the back? I'm looking for a response here. So think about it. If you jump in the subway, do you get hit and slammed into the back of the subway? Think about it for a minute. An answer. No, right? Now, it's easier. This statement seems a little more ridiculous today because we move very quickly, and so we experience very fast and different what they call frames of motion. But you have to understand, at 1664, unless you were rich, the fastest anyone had ever traveled in their entire life was when they ran. Okay? And very few people had probably stepped on anything that was moving at an appreciable rate. No skateboards, no bicycles, no cars, no trains, just horses. And horses were not cheap. Okay? So, one thing, if you've ever ridden a horse, you'll experience is if you stand up on a horse and it starts moving, you'll get thrown off. So the thought here, before Galileo came along, was that the Earth couldn't really be moving because objects in the Earth would be left behind, right? If you threw something up, the Earth, as it moved, the Earth would leave it behind. Now, Galileo actually invented a model called relativity. You might attribute that to Einstein, but what Einstein had to do was modify Galileo's relativity to be consistent with 200 to 300 years of scientific development. And we'll talk about that in a little bit, well, probably in a couple weeks. But Galileo had this idea that you should be able to transform from one description to another. Now, I usually do this in class by walking around, but I can't do that as effectively. So I want you to consider this pen's motion. All right, I think you can see me. I can see it going up in the air, so you can see it going up in the air. Now, you describe that motion, right, as, there we go. You describe that motion as the pen goes up and the pen goes down, right, up and down. So if we were all sitting next to each other, we would see that. But now I want you to, I'm going to do the same thing, but I'm going to move my arm, and we'll see if it works. It's not going to work. I can't do it well. I'll try and do it while moving. Hold on. This will be pretty bad. Yeah, no, it's not going to work. But basically, imagine I'm rolling across the room, right? The pen, as I move across the room into frame, will have this translational component to it now, right? That was a lot of rolling. And if you're looking at it from, so for the person moving, the pen is still up and down, right? If I'm in a bus or something, I still see it throwing it up and down. However, if you're looking at me move from the outside, the path of the pen now looks like this. So the question when it comes to relativity is who's right? The answer is both are right. Both this movement and this up-down movement are correct. It just depends which perspective you are, which frame you're in. And so what Galileo did is he answered this question, and he would have said, well, you're already moving with the train, which you all already know. So if you jump, the train can't hit you because you haven't changed that motion. You're still moving with the train. So from the perspective of you and the train, you would just jump up and down. However, if I were on the track looking at you in the train, I would actually see your path look like this because you're moving with the train, right? So that is how what this objection is and how it was resolved. All right? And again, perfection is, we might be holding on to too much there to make them look bad. So Galileo's experiments showed that objects in air would stay with a moving Earth, again, just like you move with a moving train. And Galileo showed that objects will stay in motion unless a force acts to slow them down. So unless there's an agent slowing something down, it won't slow down. So these were critical. So overcoming the second idea, heavenly projection or perfection, Tycho's observations of comets and supernova already challenged this idea. However, using the Galileo telescope, he saw sunspots on the Earth and mountains and valleys on the moon. This proves it's not a perfect sphere, but again, I think everyone was willing to let go of perfection. I don't think that's as spellbinding as possible. Now, what is important is overcoming this third objection, parallax. In fact, this should be in bigger font than the other ones. Okay? Because Tycho thought he had measured these stellar distances, so the lack of parallax seemed to rule out the orbiting distance. However, Galileo was able to show that stars must be further than Tycho thought. It says in part, but mainly by using his telescope to see that the Milky Way is countless individual stars. And basically, with the advent of the telescope, more stars could come into focus where there weren't any, so they could be farther away. And something we thought wasn't stars turned out to be stars, so the distance didn't line up. So that gave evidence that the stars were much farther away than previously thought, and if they were previously thought to be that far away, and you could start to get distances, that all of a sudden indicated that the parallax, which was a problem, was no longer a problem. And again, just to remind you all, the parallax is this effect of blinking your eyes, holding your finger up, and changing between eyes and watching the finger go from one side to the other. All right? So, let's see here. Galileo, also with his telescope, saw 4 moons orbiting Jupiter, proving that not all objects orbit the Earth. That's a big one, right? He just showed that something orbits something else. So there's no need now for everything to orbit the Earth to be consistent. Now, Galileo's observations with the telescope also showed that the phases, that Venus could have phases. And the fact that Venus has phases, as observed, now could not be explained with the Ptolemaic view. It could only be explained with the Copernican view. All right? Because with the Ptolemaic Venus, you should get this, crescent, new, crescent, right? But now with the sun in between here, we have a full waxing and waning Venus, and that means it must orbit the sun. So the telescope was able to give conclusive evidence that made the geocentric model problematic, and it kept adding new data. It explained the major problem first, which was the stellar distance and parallax, so it made that less troubling. So the stars weren't as troubling as planets would be in a geocentric model, and it collected brand new data that could not be explained with the Ptolemaic model, but could with the sun-centered Copernican model. A huge deal. All right. So this was not done without issue, though. In 1633, the Catholic Church ordered Galileo to recant his claim that Earth orbits the sun. His book on the subject was removed from the Church's indexes of banned books in 1824, and he was formally vindicated by the Church in the year 1992. I was in 5th grade in 1992. So even though it seems a long time ago, it's not. All right. So that's the stuff we learned. Now I want to use this chapter. We'll cover it briefly, but I want to use it to describe, to sort of solidify some of the stuff we've talked about, particularly what is a scientific theory and how we distinguish science from non-science. Again, like I said before, science is limited in what it can handle, but what it does handle, the information it does handle, it handles really, really well. And it grows and it changes. But again, scientific, I'd encourage you all to compare how Dr. Fauci presents the coronavirus with how other people in the cabinet and in the administration present the coronavirus, and you'll see the difference. It says here it can be surprisingly difficult, but again, even the book acknowledges not all knowledge comes from science, and that's okay. You'll often see these things called the scientific method. I'm not a big fan because this is not how it always goes. Sometimes you ask a question and then make observations. Usually you do one of these three activities, and then whichever one you can do will inform the other ones, which way they go. And basically, once you make a hypothesis, you can test it with math, you can test it experimentally, but in order for it to be an accepted part of a theory, you have to somehow meet all of these things. You'll have to ask a question and make a prediction and test that prediction, usually with an experiment or additional observation. And that brings us to the word theory. All right. I want to start back there. Theory, a scientific theory is a powerful collection of verified facts. All right, it's a model, it's a structure in which we look at things. This causes confusion because of the way the words are used. Sometimes people will talk about Einstein's theory of relativity as just a theory and not quite as explanative as Newton's laws of motion. Whereas Einstein's theory of relativity is actually more explanative than Newton's laws of motion. It's not called a law. They're not called Einstein laws for particular reasons, mainly because after hundreds of years of development, we knew that scientific ideas were malleable, which is that they were subject to revision, that we had not found this final explanation, which, in the time of Newton, he was like, I've discovered everything. And even and at the end of the 19th century, people had assumed physics was done and that there wasn't much more work to do in physics, and that was completely wrong. And even today, we know that relativity does have its limits. It doesn't explain everything in the universe, but it does explain more than Newton's laws. So in that sense, theories are, by definition, always up for revision and falsification. But again, in order to be called a theory like Einstein's theory of relativity, Einstein's theory, or the theory of evolution, these are all broad ideas that have lots of observations and hypotheses that are well supported with observation and hypotheses, sets of statements and things like that. So as we go forward, when we look at our hypothesis, this is what we suspect is going to happen, and it says educated guess why you think that's going to happen. And then with enough hypotheses that are interconnected, you start to get to a theory that have been verified in one way or another. But you'll notice even this slide mentions this. Sometimes we start by just looking and coming up with possible explanations. Sometimes we follow our intuition rather than a particular line of evidence. And then we collect evidence to see if our intuition is correct, or we follow our intuition until we come to a testable sort of node where we say, okay, I can test my intuition here, see if it's right or wrong. It's a little complicated. So hallmarks of science, number one. Modern science seeks explanations for observed phenomena that rely solely on natural causes. A scientific model cannot include divine intervention. If you follow some politics, there's generally this, what I think of as a sort of this weird battle that the media would like to, that TV in particular would like to think, and the internet exists between science and religion. It's always a subject I've kind of struggled with. In my mind, they serve sort of two purposes, and it's not that you can't find elements of one and the other, I suppose. It's just that one seems to me like learning how to do algebra, and the other seems like learning how to plant crops or farm. Both of these are important and have uses, but they're just different. So these intelligent design things, we often get hammered by being open-minded in the science field by saying it's not science. Well, we say it's not science because it appeals strictly to an agent or object that is beyond knowing. That violates this solely on natural causes. And it doesn't make sense to make a belief system or a faith model falsifiable. Faith is defined as, you have, when you have faith in something, you by definition aren't looking to falsify it. So in that sense, it's not, it doesn't mean there's no place for these things. It just means that when you're studying a scientific structure or idea, you can't, you are barred from having divine intervention. It doesn't work in the model. If it did, then we'd just be kind of done, and we wouldn't, anyone could, we'd devolve into fights about when divine intervention takes place, and then we get more back into philosophy. Now, again, this isn't to say what's bad or good, because it can seem like that. It's just what's science, what isn't science, and that former question often gets conflated with it, and that's not the case. But science is, again, limited with what it can do, and it's limited to what can be explained naturally without supernatural explanations. Hallmark of science 2. Science progresses through the creation and testing of models of nature that explain the observations as simply as possible. Our explanations may not be correct, but we often use this idea of Occam's razor, which is that all things being equal, the simplest explanation is the true explanation. So another way to look at that is things are as simple as we think they are until we find a reason for them not to be. So a lot of times we'll be talking about something, and you might say, well, wait a minute, could it be another way? And the answer is yes, it could be another way. But with the data we have, we choose the simplest explanation, right? So when we see, for instance, in the sun, hydrogen turning into helium, and we see the hallmarks of a nuclear fusion reaction, we say that the sun is undergoing nuclear fusion. Could it be something else? Sure, but that is now more complicated than the explanation of nuclear fusion that we have. If it is something else, that something else will eventually become the simpler explanation, and that's how we do these things. All right. A scientific model must make testable predictions about natural phenomena that would force us to revise or abandon the model if the predictions do not agree with the observations. This is falsification, and this is true. Unfortunately, some branches of science have not done themselves any favor. There's a branch of physics called string theory. String theory does not make any predictions about the natural world. It has a lot of ideas about it, but has not suggested a prediction. And anytime it could have made a prediction, it's gotten it wrong. So, but it's opened the door for other academics to question the importance of falsification. Falsification is still the gold standard of science. It's still the important part of what we do. People agreeing on something like string theory has not done us a great service, but string theory is not as prominent as it used to be. 20 years ago, like, string theory was assumed to be true. It had it to this moment, but as the models keep showing that it's just not meeting any of its predictions, it is falling out of favor, slowly. Okay, so here we get to theory. The word theory has a different meaning in science than everyday life. In science, a theory is not a hypothesis. And you'll notice that this makes the scientific theory must explain a wide variety of observations with a few simple principles, be supported by large, compelling body of evidence, and not fail at any crucial test of its validity. All right? Now, again, theories can be limited. Einstein's theory of relativity is absolutely limited. Quantum theory, absolutely limited. But in the realms in which they make predictions, they're extraordinarily precise. And in fact, quantum theory, which can sound very weird, its principles are non-intuitive and can seem very crazy, is the most precise and accurate theory, period. It is the creme de la creme of human thought in science. We'll talk a little bit about quantum physics in this class, but I won't scare you too much, promise. Well, maybe I'll scare you a little bit, but we won't have to do too much math. Okay. So we do that. All right, so we can take about 5 minutes. Don't go too far or anywhere. I want to upload the next chapter so that we can sort of continue on. And if you have any questions, now would be a good time while I get the next bit of the lecture set up. So, oh, geez, I forgot here we go. What? All right. So I have to So I'm going to stop sharing that, and I'm going to remove these files, and I'm going to get you, and I'm going to put you here. And this will take a couple minutes to upload. Everything clear? Any questions? Any thoughts? Or yeah. So I'm gonna set up. I seem to have. I thought I did it last night. Realized when I got here, I will be setting up a weekly repeating meeting for our class so that we don't have what happened today happen last time, so that students can join the room if I don't get here. Get to my computer on time, because I think they joined a room that I didn't create, and then I wasn't there. So unfortunately, everyone has to join the room I create, and that's what I think the problem was with some of the other students. So we should have that fixed by next time, but keep in mind, this will be recorded and the movies will be accessible, so everyone will be able to watch. Okay, so the whole thing. All right, let's see here. Let's see how this file transfer went. It is there. Hold on. Okay. So switch to follow the speaker mode. No. Okay. So let's see here. All right. All right. Just give me 1 second while some of this is loading. I want to find some things for this demonstration we're going to do. So so again, like I said, three minutes or so. Back. All right, I'm back. Allow share video and hold on. Oh, okay. Let's not allow. Hold on. Okay. Seem to have erred. All right, I'll have to use that. Oh man, that's going to be tough. Okay. So there's a video I really like to show here that's important. And I seem to have disabled that. Hold on. Let me see here for a minute. Oh, God. All right. Hold on. Polling. Okay. So I have my permissions. All right. So now let's share the screen. Oh, okay. All right. This might be okay. Hold on. Mozilla Firefox. Let's allow. Okay. Can everyone see the screen I'm sharing? Yep. Okay. So we're going to want to try and do that. Okay. So let's see if we can get that to work. CUNY login. Let's see if is that a specific Mozilla screen? So if I can do that, then things might be a little. Hold on. All right. We'll figure that out when we get to the video. Right now, we're going to share files. Lecture 4. We're going to share this now. So hopefully, when we get there, that will work. But you know, we'll try and we'll try and see to make sure that that works. So right now, what we're going to do is, now that we've ended with Galileo and science, is now we're going to get into some physics. Okay, and basically, physics is the study of motion. All right. So first, we'll describe motion, and we'll describe the difference between motion and weight, or mass and weight. All right. Those are the things we'll want to do. I'm noticing this thing is not moving. Okay. So yeah. So we want to do that. As we look here, we need to be as precise as possible with our definitions. All right. And we'll have some stuff here like speed and velocity. These are two different types of quantities. All right. So really, they forget one here, which I'll write. So the first one to write is position. Position, which is position is a scalar, like speed, and displacement that's supposed to be displacement, but displacement is a vector like velocity. So velocities, you'll notice, speed just has one number. This is called the magnitude, and the velocity, it just has this one number called the velocity, or called the magnitude. The velocity has both a magnitude and a direction. All right, so vectors have to have both, and this can make them very counterintuitive, because in vectors things can change even if the magnitude, or if the magnitude can stay the same, but the vector can change if the direction changes. So there's two independent things moving. Now, speed or velocity is defined as a change in position or displacement. Well, speed would be position, or velocity would be a change in displacement over time. All right, and acceleration is a change in velocity over time. You'll notice that's where you get this meters squared. Okay, so With that being said, oh, okay, that's too bad. So basically, understanding the difference between these things, these two can be easy. Understanding the difference between these two can be pretty hard. So if you've ever ridden a roller coaster, you might want to think, what moves faster, a roller coaster or the 7 train? Think about it for a minute. What do you think? Seven train. 7 train actually does move faster. Which one will make you puke faster? A roller coaster or the 7 train? Or which one are you more likely to vomit on? The roller coaster. Good. If you actually look at roller coasters and look at how they actually move quite slowly as far as speed goes, but their directions change very rapidly. All right? They're going all over the place and get dizzy and get sick. Acceleration is what you feel is not happening very often, but in a car, when someone slams on the gas, right, and you go backwards like that, that's the feeling of acceleration. However, once you're not speeding up or slowing down, you're no longer accelerating. So if you're moving straight down and not changing direction or speed, you could be moving at 110 miles per hour and not accelerating, right? As long as your direction stays the same or your distance or your speed stays the same. Now, you'll notice here, though, if you turn, right, if you're driving really fast and you turn, all of a sudden the car can lose control or go out or spin out. So when you change direction, you can have just as much gas in there, and you can, bad things can happen. Or rather, it's not that bad things can happen. Bad things can always happen in the car, but you're accelerating, right? So it's a little harder to describe. It's a little bit harder to describe more than that without being in class and dropping things. But basically, you can see it for a car, but now we want to look at it in terms of falling objects. So we have this ball that is dropped off this building, and it has a motion. It starts accelerating. So does anyone want to give a shot as to what is causing the acceleration? It's on the slide, in case you can't see it, but take a look and chime in. Oh, am I not seeing it come up here? Anybody out there? All right, well. Oh, can you hear me now? Okay. So what I'm asking is, I'll type it too. What is causing the ball to accelerate once it's dropped from the building? Dropped from the building. That was what I asked. So gravity, good, but what is gravity? What's causing the gravity? No, the gravity is an acceleration. The weight of the Earth, good, or the mass of the Earth is the better answer. But yes, the mass of the Earth causes gravity. I'm just typing for those of you who can't hear. So but you'll be able to hear a little later. So yeah, so gravity pulls down. If you don't believe me, jump, take a jump up, and you will not float away. I promise. Gravity, the Earth's gravity, will pull you down. All right. So now, in order for this to be true, though, in order for this to be acceptable, we have to come to the fact that the Earth can't pull on different things at different rates, right? The Earth would have to pull on the same objects at the same time. So I have these two objects, and we'll see which one falls first, although we can't see the ground. Well, you can already see the paper still falling. So it seems like this is wrong. But you'll notice something that's here, ignoring air resistance, it's the same. And so what I want to show you is that this experiment was done on the moon, and we're going to try sharing the screen again, so let's see how that goes. All right. Without everything going, select a window, so let's do Firefox again, and we'll allow. And so I'm going to go to YouTube here. YouTube. I did mean YouTube. All right, and we can search from YouTube, hammer feather drop. All right, so we're going to watch this, and hopefully this will, you can make it look on your screens, however will work.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, I have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
All right.
Was correct in his findings.
Let's watch that part of it again.
Where would be a better place to confirm his findings than on the moon? And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Gotta love the 60s. All right, share files.
Superb.
Share now. Okay. So let me stop the YouTube from
Hi, my name is
going, and then we just need 1 second to get back to you all. All right. Okay. All right. So, what did you all think of that video? Thoughts? It's pretty cool, huh? It looks a little, well, it's from the 1960s, so everything's going to look weird. If you want to look at moon landing conspiracy theories and see why we actually did land on the moon, you will hopefully be very convinced. Most of the, actually everything I've seen has been pretty easily disproven. But keep in mind, that was not the first landing on the moon, that was the 4th or 5th one. So they had time to think about what they wanted to do and make it look cool. Also, clearing out that much vacuum is hard on a big stage like that. So I don't think it could have been done in the 60s, let alone now. They both the text movements fall at the same time. Right. It's the air. Right. The air resistance is why we don't. Was why the paper wouldn't fall. But the thing is that the point of doing that is to look at. Is to see, ask yourself, why do things behave differently than you expect them to? And we have to remember the idea of air molecules, or what the understanding of what a molecule was, or what air was still quite a bit away, a ways away as far as understanding it the way we do today. So all objects fall at the same speed on a body. Right now, the body we're on is the Earth. So that will give us the speed at which they fall. So the acceleration near Earth, is approximately equal to 10 meters per second squared. All right. So that means that after 1 second, your velocity is 10 meters per second. After 2 seconds, your velocity is about 20 meters per second. And after 3 seconds, 3 meters per second, and so forth. Now, air actually plays an interesting role in creating what we call terminal velocity, because believe it or not, if we completely ignored air resistance, or if there were no air resistance, rain would be quite lethal from the height at which it falls. But because of air resistance, it only, it falls safely and doesn't feel like a machine gun bullet being fired at you. So air resistance is important but not negligible. All right. So, yep, they were just going to show that's the hammer feather drop experiment. So we have to learn some of the language of physics. All right. So momentum. Let me look here. So momentum, which is here, all right, is mass times velocity, and force, Newton's second law, which we'll see, is equal to m times times acceleration. All right, and if you sort of move these apart, and you remember that acceleration is equal to m, the change in velocity, over the change in time, you can actually see that force is equal to the change in momentum, which is usually given with a p, why I do not know, over the change in time. What I want to make clear here is that force and momentum are very much linked. These are vectors. I want to be careful with that. Don't worry so much about the math part, like you won't have to do this. I'm just sort of showing you how they relate to each other. All right. Net forces change momentum. All right, and that's, you can see just how that works here. And forces were really defined well or rigorously by using Newton's Newton's laws. So Newton really came up with a way to describe them. Going forward. So, oh, I don't want to do this. So now we want to go into the difference between weight and mass. All right. So mass is, hold on. Mass will tell us how much of something there is, the amount of matter in an object. So basically, you can get your mass by putting all the atoms in your body, collecting them, and counting them. Now, this number doesn't change. If you have 10 bazillion atoms in Earth, you have the same number of bazillion atoms. Bazillion is not a real number. Hashtag fake number. Atoms in Mars. All right. Let's say if you have 10. If you want to be technical about it, because we're in a college course, if you have 10 to the 24 atoms in Earth, you'll have the same 10 to the 24 atoms on Mars. All right. No big deal. And when I mean 10 to the 24th, I'll be explicit here. That's 10 to the 24th power. All right. We'll call that number of atoms in you. Okay? That's probably a gross overestimation, but let's just say it's true. You'd still have the same number as you move. Now, weight is a force. So it'll be the product of your mass times the acceleration of the body you're on. So with Earth, to get your weight, you have to multiply your mass times that acceleration. Okay? Now you can actually change your weight pretty easily. If you go into an elevator, as the elevator starts to accelerate up or down, your mass actually changes. And if you're on a scale, you will see it move by 2 or 3 pounds. And of course, if you're on that scale, and you're, say, at the top of the World Trade Center, and they cut the cord, as you fall down, you will be weightless. So you might be asking, what is my sensation of weight then? Your sensation of weight is actually the sensation of the force pushing from the floor back up on you. All right? Because you'll notice, as you're falling, gravity is still pulling you down. It's what's accelerating you. But you don't have a surface pushing you back up, which is what causes your sensation of weight. All right? I hope that makes a little bit of sense. Anyone want a clarification or part of that? What do you think about that? The difference between mass and weight. Everyone's good? Okay. All right, I got one. I'll take it. I didn't get a no, which is really what would cause me to stop and do that. So don't be afraid to say no. So, going forward. Now, why are astronauts weightless in space? This might be one of the few slides that's actually easier online than in class, because I usually start talking to you guys and don't point out this stuff. But let's think about what happens the faster you're able to run off of a tower. So if you're able to run, or you jump off, you'll fall straight down, right? Now, if you can go a little faster, you get a little farther. And say you had like a bullet speed, and you could go farther still. But now imagine you have a giant rocket on you. As you have a rocket, you're so fast that as you fall to the Earth, you keep missing the Earth. So when you're here and you fall down, if you go fast enough, you clear the Earth and you move, and the Earth isn't there yet. You're faster than the Earth is moving. And then, but you'll notice that instead of flying just far away from the Earth pulls you back and keeps trying to bring you back to the surface of the Earth, but you keep missing it. So being in orbit can really be thought of as constantly falling, but you keep missing the Earth because it's not where it was, you know, when you fell. Because now you're moving at speeds comparable to that of Earth. All right? And you'll notice this is an interesting North Pole view. So you see the Northern Hemisphere. This should, the world looks very different from the Northern Hemisphere. You'll probably notice Greenland here is the size of Mexico, and some other interesting things. The United States all looks really weird and different. You still got Florida there. What you may notice, which is surprising to some people, is that as you come up the east coast of the United States, you're pretty much still west of South America. Mercadian projection maps are very disorientating as far as whatchamacallit. They're disorientating as far as getting an intuition for where geography actually is. And you'll notice that when you fly to Europe, for instance, you don't really, when you cross the Atlantic, you cross this way, not like on a map where you would go this way. All right, fun times. So we've got that done. So now that we have a basic study for like what's there, we want to know how Newton's laws of motion formed what we had before, what Galileo and Tycho Brahe and Kepler had before Copernicus, and how that comes into our first model of physics and how that's used to explain things. So as we go forward, How did Newton change our view of the universe? This is Isaac Newton. He's, I think, one of the last scary-looking dudes we have. You'll notice when he was born, 1642 to 1777. 1660 is a good enough time to sort of start the edge of the beginning. So we're really not even 400 years old in terms of modern discoveries. He realized that the same physical laws that operate on Earth also operate in the heavens. That is, there's one universe, and without reason to think that there is a different universe, everything should work the same. So he discovered the laws of motion and gravity. He basically created the first scientific theory and framework by which he can make predictions in a connected framework. And much more, but unlike our Bed Bath & Beyond or our and more usually, he really did a lot. He did groundbreaking experiments with light, the first reflecting telescope, which is a type of telescope. Galileo made a refracting telescope, and he invented calculus, although he did that at the same time as a German philosopher named Gottfried Leibniz, and they often, I don't know what all this stuff is here. That's kind of weird. I'm gonna go back. I'm gonna go forward and see if all that weird stuff disappears. Yeah, good. Okay. So Leibniz also invented calculus. The study of calculus is really just the study of the rates of change and instantaneous change versus long-term change. It's difficult for sure, but that's all it is. And this wasn't even what he was knighted for. Sir Isaac Newton, if you look here, the Sir part actually comes from his work as the head of the British Mint, and he came up with ways to thwart counterfeiters and ingenious ways of making money that were hard to counterfeit at the time. So that's actually why he got knighted, for his services to the crown. It's usually why you get knighted. But Newton is a pretty impressive dude. If you were to make a list for scientists and mathematicians of the top sort of thinker, the top 10 list would be very different for almost everybody, except Newton would universally be at the top 1 or 2 there. Some people would put Leibniz above Newton, but a lot of people will put Newton as number 1. So you can, if you're ever wondering who the smartest scientist who ever lived was, this is usually the guy. He gets this credit. He gets this credit because even though science has changed, the structure by which we do science hasn't changed. And he came up with that structure. And he sort of single-handedly, in a way, brought us from an Aristotelian, from an empirical sort of view of the universe, which is very classical, even though Kepler found that the universe behaved in these new ways. It was still sort of empirical. There was no model behind it. And Newton created like this scientific model. And basically, models are still kind of done this way today. I mean, it was a huge, huge leap. Very strange guy, not a nice guy, Isaac Newton. Not known for being friendly. Very much by himself. He often, you'll notice he lived to the ripe old age of nearly, I guess, past 80, 85. And he's one of his he was very proud of his purity. I'll let you figure that out that means. You can Google it. When he died. So very religious, very much an alchemist is how he would describe himself. Person of the times. So interesting guy. But let's look what he did. Oh no. So Newton's first law of motion. An object moves at constant velocity unless a net force acts to change its speed or direction. So Newton's first law is more commonly thought of as objects in motion stay in motion, and objects at rest stay at rest unless acted upon by an outside force. Now this is a pretty, sort of something we learn in grade school and take for granted, but it's pretty counterintuitive. If you don't believe me, let me see if I can get the zoomed out here to the desk. This is going to be bad. The camera's going to fall. and I'll be sad. Hold on. It's probably getting muffled. But if you look at this pen, hold on. Where's the pen? If you look at this pen and I get it moving, it doesn't keep moving, right? It stops. That's not going as well as I thought. Not at all. But if you just pick up something and roll it on the floor, did it keep moving forever? That's my challenge to you. I'll give you all like 30 seconds to do it. Not that I can hear, but roll something or move something. Set it in motion. You'll notice it didn't stop, right? So in order to, you really have to have a thought. It hit your wall, right? Something stopped it. A highlight, anything's fine. Yeah, a highlighter. It does not roll forever. And so, but you have to realize when Newton's thinking about this, no one had ever been to space. No one had fallen in a point to be weightless. These experiences hadn't really happened. Good. And it stopped somehow, right? It's not keep going straight. It either hit something, or it stopped, or something happened to make that object stop. So everything Newton ever saw stopped. But to come up with this idea is really interesting because what he's saying is that if something changes its motion, I must be able to find a force that stopped it from moving. So in the case of the door, it's a wall, right? The wall pushes back. That's kind of easy to see. But if you rolled something and it didn't hit anything and it stopped moving, that's another force that we call friction, right? That stops those other things from moving. With my pen, for instance, it would be, it wouldn't have enough force to overcome the pen clip, right? So it just stops. And if I try to make it slide, friction also is the reason that will cause it to stop. So it's a pretty interesting insight. Oh, I hope the Blistex didn't roll under the fridge. Yeah, no, I know we're getting towards dinner time. And I'm not going to keep us I won't think I'm going to keep us till 7:40. I think I'm going to call it at about 7:20. So that will be, don't worry too much. I'll need to take a picture of the attendance first so that I can update that tomorrow. I'm getting hungry too. So, but the point is that Newton's first law and Newton's laws will apply to spaceships and baseballs. Separate theories or laws or a separate theory doesn't need to be invented to handle each different object. So here we go. So Newton's law, force equals mass times acceleration. So what Newton's second law does is it establishes a force. In class, it would be 6:45, but we'd also have a lot more questions. And no, class won't be over. I mean, so basically, this is a good question. Class may be over at 6:45 sometimes, but we are making a lot of good headway because the question asking isn't quite as dynamic. But that's not your fault at all. It's the delivery. So I don't want to be like I'm accusing anyone. You guys are doing really well as far as questions and asking questions and stuff like that. It's just not as good as in person for doing that, I think. Especially in this class, I think it's easier to get distracted by something or not be around. And again, that's really nobody's fault. It's just kind of is what it is. It's a limitation of this distance learning to keep ourselves safe from coronavirus. Well, you guys safe, I think. I think it might be too late for me in that regard. But don't worry, these symptoms are 2 weeks old already. I'm if anything, coming out the other side. Last week was not good. But that being said, we normally tonight we would have done the lunar phases activity, and our activities are probably going to be, I'm probably going to give you links to do them so that you do them offline, and then write about them. And then we might use time like to talk about them or ask questions and things like that. Okay, so it's not going to be, it's for instance right now, if I'm being honest, if this were as our second week of class, and the fact that we're canceling the presentations, we're doing we're kind of ahead. I usually end the second week at the hammer feather drop, so we're getting pretty far ahead. I don't want to not do too much time, but like if we were in class, we would have stopped well, actually, we would stop like almost right about now, time-wise, regardless of where we were, and go on forward. But a lot of that is also the questions. It's hard for me to do my demonstrations and have them be effective, and to like move around the class and talk. So that sort of cuts that stuff out. So we're sacrificing clarity with the distance model. I hope I'm not rambling too much about it, but that's kind of where we are with that. And I kind of feel bad about it, but the good thing is we're kind of marching ahead. So we're where we are where I expect to be, or we're much farther than I usually expect to be at this particular time. So yeah, we're okay. I don't know, and 3 hours is a long time. I don't think we need to. I think distance will allow us to be a little more flexible, and I have a feeling how we do this will change a little bit too as we go, and as we see what works and what doesn't. So I hope I've confused you about how the rest of the semester is going to go. I will still be here, and I'll set up a room that I create so that we won't have people going through. Next week will be less confusing than this week, I promise. And hopefully, as we go forward, we'll do the best we can. So we will only meet Mondays. Yeah. That's the time everyone sort of has carved out for it. That was the time you registered for. I do feel that's important to maintain, is that respect the registration schedule. Yep, 325. There was an issue today. I was here at 325, but some students, I think, created a session. Or my hypothesis is that some students created a session, and the session, I created another session, so there were 2 sessions, and the only one that you're going to see is the one I create. So I wouldn't join it. Only a moderator can create that one. So, oh, are you saying something? I hear a microphone.
Oh yeah, that's me. Cause when I first went onto Blackboard, it was a different course room, and it was like about 10 students, and it was
Yeah.
all quiet. And then I backed out and I refreshed it, and then I saw the other one, and I'm like, okay, so who's the moderator? And then I saw it was you. So I was like, okay, so I'm in the right chat.
Yeah. So I'm going to set one up so it'll just be there, and it'll be there 15 minutes before. But the class wasn't canceled, and it will all be recorded. Everything we did is recorded. So if you miss something, it'll take a while. It'll take probably till tomorrow for the video to show up, because that's to process. And there should be 2 videos for this course, but you should be able to download the video and watch it and do anything you want with it. Okay?
Oh yeah, okay, I got it.
All right, no problem. So hopefully that makes sense of some stuff. We will let's sort of continue on for another 20 minutes or so, because it has been a lot today, right? It's been a lot. It's almost 3:30. Wait a minute. We go to 6:45 or 7? Oh no, we do go to 6:45, don't we? I got confused. I thought we had to go to 7:45. Let's stop for today then, and not do that. Holy moly! I got confused. I'm sorry about that. Yeah, no. We went way over time. I apologize to everyone about that. I thought we had to go till 7:45. Woohoo! We have done way too much for today. So we'll continue our discussions on Newton's law next week, okay? And we'll also do an activity next week. I'll figure out how that goes. My office hour technically starts, so because it's mostly for you guys, I will stay in the chat room. If you have questions, you can turn your microphones on and video on if you like. But I'm running my office hours mostly through Skype. So I will turn my stuff off here if I get a Skype call, or I'll step out. And yeah, you can let me know. So Skype, did I get any Skype calls? I don't think I got any Skype calls. So yeah, so I'm available for office hours, and if you have questions, cool. Otherwise, I gotta take a picture. Don't leave yet. I'm gonna take a picture of where did I put see, this is why I brought the phone, to take the picture of the attendance. Hold on. Picture, photo, let me get the attendance. And and if you want to Skype hold on, let me send you the email. It's just my LaGuardia email, which is on the syllabus, which again will be updated. So it'll be JQLANT. Hold on. The Skype email is coming at gmail.com. No, that's wrong. Hold on. I got confused. It's a good thing I didn't push the button. So if you use that Skype email, you should be fine. Okay? And you can, I'm going to stop the recording now, and that should get the second file processed.